All right, let's look at some Wiki 11 examples. So if we have a population that has a mean of 200 and a standard deviation of 50, a sample size of 100 will be taken and the sample mean x bar will be used to estimate the population mean. What is the expected value of x bar? What is the standard deviation of x bar? Show the sampling distribution of x bar. And what does the sampling distribution of x bar show? Well, we know that the mean is 200, so we know expected value is equal to the mean, so that gives us 200 for our value here. Now, we have to use equation 7.3 because we're going to need sigma x bar is equal to sigma divided by the square root of n, where n is equal to 100. The sigma was equal to the 50, so 50 divided by the square root of 100 is equal to 5. Now let's show the sampling distribution. Well, this is going to be a normal sample with sigma of x bar equal to 200. We found that there, and sigma x bar is equal to 5, which we found there. Now, what does the sampling distribution of x bar show? Well, it shows the probability distribution of all possible sample means that can be observed within random sample size of 100. Now, this distribution can be used to compute the probability that x bar is within a specified plus minus 0.05 or whatever from mu, and we'll be seeing that here in a little bit. All right, so the mean annual cost of automobile insurance is $939. Assume the standard deviation is sigma equals $245. A, what is the probability that a sample of automobile insurance policies will have a sample mean within $25 of the population mean for each of the following sample sizes, 30, 50, 100, and 400? And then B, what is the advantage of a larger sample size when attempting to estimate the population mean? All right, so we're going to have to use the z equation. So it's going to be z equals the x bar minus our mean, which we have up here, which is 939, divided by sigma, which they gave us was 245, and divided by the square root of n, which is going to be varying between 30, 50, 100, and 400. All right, so they tell us that it's going to have to be within $25 of the population mean. So $25 within that. So instead of actually doing each of them plus 25 and minus 25, if we just say that the difference here is going to be 25, and then we just, whatever value we come up with in for the z, we look at the plus and the minus value in our z table, then that will get us what we need. So what I'll do here is I'll explain what I'm doing along the way. Ballpoint pen. So like I said, it says it's going to be within 25, so we know that this difference is going to be within 25. Everything else is the same, except for now we have to plug in 30. So our first one is n is equal to 30. We simplify that and we get 0.56. Now, since it said it's within plus or minus 25, we're going to look at the plus and the minus of 0.56. So we just look both of those up in our table, and we should get the 0.7123 for the upper, 0.2877 for the lower, and we subtract those, and our probability is 0.4246. We do the same thing for 50, we get 0.5284, for 100 we get 0.6922, and for 400 we get 0.9586. Now, what is the advantage of a larger sample size when attempting to estimate the population mean? Well, if you look at our probabilities, there's a higher probability that we're going to be within the 25 of the range. So with the smaller one, we only have a probability of 0.4246 that it's going to be within that range, whereas the other one we have probabilities 0.9586, so larger sample size is just giving us a better probability that we're going to estimate that population mean correctly. Now 32, population proportion is 0.40. A sample size of 200 will be taken, and the sample proportion p bar will be used to estimate the population proportion. What is the probability that the sample proportion will be within plus or minus 0.03 of the population proportion? And B, what is the probability that the sample proportion will fall within 0.05 of the population proportion? Well, what do we know? Well, like I said, we know the population proportion is at 0.40, so that's going to give us this. We had a sample size of 200, and so we can just plug everything we know into the sigma sub p, so the 0.41 minus 0.4 over 200. Simplify all that, we get 0.0346 for sigma p. Now, we can do as we did before. We know that the difference is going to be within 0.03, so what we can do is we can do that again. We can do the plus or minus 0.03. So once we find the plus, which is going to be the 0.87, we can also find the negative of it, and then we just subtract the two. And all we do here was, for z, we plug in the difference, which they told us in this case was 0.03. We have our sigma p is 0.0346, so that's our denominator, so we get that 0.87. And then we also look at the negative 0.87, and we find those probabilities, and we subtract them, and we get the probability is 0.6156, that it's going to be between 0.37 and 0.43, which is if we take 0.40 plus 0.03 and 0.40 minus 0.03. And so that's where those two values are coming from. We're just adding and subtracting that 0.03. Now, similarly, for the next one, all they want us to do is do the 0.05. So really, all we have to do is change the value here, find the number here. That's going to be the 1.44, and then we find the plus probability and the minus from our table, so 0.9251 minus the 0.0749, and that gives us the probability of 0.8502, that it's going to be between the 0.35 and the 0.45, which is going to be the 0.40 plus and minus 0.05. Now for 38, 42% of primary care doctors think their patients receive unnecessary medical care. A, suppose a sample of 300 primary care doctors were taken. Show the sampling distribution of the proportion of the doctors who think their patients receive unnecessary medical care. B, what is the probability that the sample proportion will be within 0.03 of the population proportion and then 0.05 of the population proportion? And what would be the effect of taking a larger sample on the probabilities in part B and part C and why? So you can see that a lot of these problems are starting to look very similar. We're going to look within 0.03 and 0.05, what happens if we do larger samples and things like that. So hey, suppose we had the 300 primary care doctors. So we're going to have N is equal to 300, and our P is going to be that 0.42. All right, so the expected value is going to be 0.42. The sigma p, now we just put that 0.42 in here, and the n was 300 we saw, so that's going to give us the sigma p is 0.0285. And so that's basically our part A. It's a normal distribution with the expected value of that, the sigma p of this, and that's our setup for the sampling distribution. Now B, what is the probability it will be within 0.03? Okay, again, we just know that the difference is going to be 0.03, so we just have to take that value, and then we're going to look at the plus of it and also the minus. And so we take the 0.03 divided by our sigma p, which is 0.0285. That gives us a 1.05. So if we look at that on the table, that gives us 0.8531. The negative of it should give us 0.1469. We subtract those, and that gives us a probability of 0.7062. And again, it's within 0.03, so we take that 0.42, subtract 0.03, we get the 0.39 as our lower end, and if we add the 0.03, we get the well, that should be a 5 on the upper end there. Apparently the book was wrong. Okay, so so they have that value. Now within 0.05, all we do again, all we change is the 0.05 here. We're going to still do the plus and the minus once we find that z value. So that's 0.9599 and 0.0401. Plug those in. So here, I'm not sure. They weren't paying attention to what they were doing here. So just note that those are supposed to be within the 0.05. So the 0.42 minus that, so that would be the 7. And then this would be the 47. Okay, and so that gives us a much higher probability of 0.9198 compared to the 0.8531. Now, the last question is, what would be the effect of taking a larger sample on the probabilities? Well, if you get a larger sample, that's going to be a much larger number. Say we put 500 in here. Well, that's going to make this smaller. If we make that smaller, then, it's going to make the probabilities increase because we're going to change everything. And so this would be higher, and then this would be higher due to the fact the way it changes everything here by it's going to make that smaller. And when you make this smaller, that makes it bigger. And so therefore it makes the overall improbability larger. All right, so the U.S. News and World Report publishes comprehensive information on America's best colleges. Among other things, they provide a listing of their 133 best national universities. You would like to take a sample of these universities for a follow-up study on their students. Begin at the bottom of the third column. So note here, it's the bottom of the third column of a random digit in table 7.1. Ignoring the first two digits, so we ignore the first two digits in each 5-number group, and using the 3-digit random numbers beginning with 959, read up the column and identify the number from 1 to 133. Now this is a key because a lot of people on the quiz last time missed this because they forgot to limit the max value to the largest number in the question. So here we can't go any number above 133. So if we find something that's 134, we have to ignore that, go to the next random number. And it's of the first 7 universities to be included in a simple random sample. Continue by starting at the bottom of the 4th and 5th columns and reading up if necessary. So once we get it done with the 3rd one, start back at the bottom of the 4th, read up, then go to the bottom of the 5th, read up, and keep going like that. So we had to start at the bottom of the 3rd, and we want to ignore the first 2, so we don't worry about those. We're only worried about that last number. So 959. Well, can we use that? Well, it's greater than 133, so no. Then we have 177, 389, 354, 203. So here is one, 122. The 987, here we have another one, 99, 298, 191, 430, 935, 655, 613, 215, 254, 550, 836, 190, 902, 835, 790, 865, 436, 744. Go down to the bottom, start up again. 607, 294, 324, 157, 516. Here we go. Here's another one, 25. So now we've got 3 so far out of 7. 962, 528, 678, 860, 165, 801, 915, 55. That will work. 498, 835, 157, 351, 588, 447, 290, 122. But we've already got 122 down here, so we can't use that. 911, here's one. 115, also 102. So that gives us 1, 2, 3, 4, 5, 6. So now we go back to the bottom, 244, and then here we go. Here's number 7, which is 61. So if we look at those, this should give us the same values we have right here. Okay, so that's how you use the column. You can't use the numbers that are larger than the 133, but you can use all the numbers smaller, but you have to keep going until you find all of them. All right, so 46, after deducting grants based on need, the average cost to attend the University of Southern California is $27,175. So that's the average, or the mean. Now assume the population standard deviation is $7,400. Suppose a random sample of 60, so in 60 USC students will be taken from the population. What is the value of the standard error of the mean? Okay. B, what is the probability that the sample mean will be more than 27,175? C, what is the probability that the sample mean will be within 1,000 of the population mean? And D, how would the probability in part C change if the sample size were increased to 100? Okay, so what is the value of the standard error of the mean? Okay, we know that this is mu and this is sigma, and we want the sigma sub whatever the x bar or however whatever variable we're using here. So we're going to use equation 7.3 again. So we just take our sigma 7,400 divided by the square root of n, which was 60, and that gives us 955 for our standard error of the mean. Now the next one, what is the probability the sample mean will be more than the mean? Okay, well, it's basically what is that line now, that's the mean, and what is the probability that it's going to be greater than? Well, that's half, because remember, this is a whole thing is 1, half of it split on the upper half, and there's also half on the lower half, so both of those are half, and so we could automatically calculate that and as a half, or we can go through our whole process and take 27,175 minus 27,175, which gives us 0, divided by the 955 we found here, and that gives us 0. And so if we look that up in our book, well, that gives us 1/2, which is what we already knew from here. Okay, and then they also are nice to kind of explain that as well in the answer key. Now C, they ask for within 1,000. So we can do as we've been doing, we can do the plus or minus 1,000 by taking, and the 1,000 is our difference here, divided by our sigma x bar. And so that's going to be the value, and we're going to look at the plus and the minus in our table. So 0.8531 is the plus, 0.1469 is the minus. We subtract those, and we get 0.7062. And so within 1,000 of it, so we're going to go minus 1,000, so that'll be 26,175. And we'll also go greater than, so it'll be the 28,175. Okay. And what would happen if we change the sample to 100? Well, we just have to do our whole calculation again from the start to find what that 955 is now. Well, it's 7,400 divided by the square root of 100, which is going to be 10, so it's 740. So we've changed that. We plug the same thing in. Now we're using 740 instead of the 955, so we get the 1.35. So we look at the plus and the minus, subtract those, and now we get 0.8230, and it does what we expect it to do. Higher sample size gives us a better probability. All right, so here we've got number 52, and as soon as something on my screen disappears, I can read it. All right, advertisers contract with internet service providers and search engines to place ads on websites. They pay a fee based on the number of potential customers who click on their ad. Unfortunately, click fraud, the practice of someone clicking on an ad solely for the purpose of driving up advertising revenue, has become a problem. 40% of advertisers claim that they have been a victim of click fraud. Suppose a simple random sample of 380 advertisers will be taken to learn more about how they are affected by this practice. What is the probability that the sample proportion will be within plus or minus 0.04 of the population proportion experiencing click fraud? And what is the probability the sample proportion will be greater than the 0.45? So what do we know? Well, 40%, so that's going to be our P bar, 0.4. N was 380 advertisers, and we're looking for that sigma P bar. So we're looking again for equation 7.3. All right, so first off, what do we have to do? We're not doing 7.3 this time because we're having the proportions, never mind. So we have to actually use the 0.4 times the 1 minus 0.4 all over the N, which is 380. That gives us 0.0251, and we want it to be within 0.04. So again, we just are going to use the 0.04 up here instead of how they're doing it here. We're just going to use the 0.04 because we know that that's going to be the answer, and then we just look at the plus and minus values. Plus and minus values and combine their z, and so that's going to be the 0.9441 and the 0.0559. Subtract those, and we get the probability of 0.8882. And that's what they did here, except they showed it longhand. They showed the 0.44 minus 0.40 over the 0.0251, and then the 0.36 minus a 0.04 divided by that and getting the negative 1.59. But we already knew that those were going to be just opposites. And so then they just showed that, they took that, which basically what we've been doing. The 0.4 minus 0.4 is 0.36, plus 0.4 is 0.44, and then we have that. So we've been skipping a lot of these steps along the way because on our first problem, we made it a lot simpler. Now, and second part, we want to be the P bar greater than or equal to the 0.45. Well, I drew a picture here. So that's 0.4, that's our mean. 0.45 is somewhere over here. So what we need to do is basically find whatever this whole area over this way is and take 1 minus that to find what this area over here is. And so if we plug it into our thing, we have to find what the z-score is. So P bar is going to be the 0.45 minus our P, which we found was the 0.4, divided by our sigma P, which is the 0.0251. That gives us 1.99. So the greater than the 0.45, which is this point, if we put that into z values, that's going to be greater than the 1.99. So 1 minus that value gives us the 0.0233. So this area over here is very small compared to the area over here. So it's really not drawn to scale, but it's kind of easy to see 0.4 to 0.45. Kind of looks like it shouldn't be too big, but in reality, it's huge. Okay, so that's all I have for this week. Hopefully those will help you. Thanks.